Hello, it's Scott Manley here, and today I'm looking at a bunch of questions from my backers over at Patreon. And I'm going to say I put this on hiatus for a few months, partly because the questions were all over the place and it was sort of soul crushing trying to find where all the questions were. But yeah, I am now rejuvenated and ready to start trying to answer your questions with some detail. So, yeah, the first thing we have is from Russell Nelson, who asked, how long does max Q last? And I want to also combine that with David B. Hill, who says, we hear a lot about rockets passing max Q during initial ascent, but we don't recall hearing any discussion about what Q is actually measuring. So, Q, or Q is the dynamic pressure, and therefore max Q is when the dynamic pressure reaches maximum, right? So dynamic pressure is if you've got an object moving through the air, then it's feeling more air pressure on one side than on the other, and that is dynamic pressure because it's related to motion. So the units of Q are pressure, pounds per square inch, or pascals, or whatever else you want to use it. Inches of mercury. Yeah, let's just use that, right? Now, what typically happens is the rocket is taking off and it's accelerating upwards through the atmosphere. And as it's accelerating, it's experiencing increased drag because it's moving faster and faster. But also, as it really starts to get going, the atmosphere starts getting thinner and thinner, so it begins to drop off. So you have this phenomenon where it gets higher and higher, peaks out maybe around the 1 minute mark, and then begins to fall off until you end up in the upper atmosphere. So for something like the Falcon 9, the maximum dynamic pressure, based on, simple calculations of altitude versus speed that they helpfully give us in the telemetry, puts it at about 30 to 40% of an atmosphere. And when you consider that the fairing on the Falcon 9 is about 5 meters across, that's a cross section of about 20 meters, so that's about 80 tons of drag. Now, typically max Q is like of the order of a few seconds, but the whole curve does mean that it's experiencing this high dynamic pressure for several tens of seconds, and the vehicle obviously needs to be able to handle this. And in particular, the thing that's most likely to, or the thing that's really experiencing the force, is going to be the fairing. So you want that to be able to handle these loads as much as possible. Now, interestingly, since we're talking about the Falcon 9, it has a second max Q. A lot of people don't realize that because, of course, Falcon 9 core comes back down to the launch site and it falls down through the atmosphere, and it is going very fast. In fact, it's going faster at lower altitudes than it is on ascent. So Falcon 9 max Q is actually on descent when it's lower in the atmosphere and going faster. And that can peak at about 1 atmosphere. That's 10 tons per square meter. And you got to realize the booster is coming down and it actually goes kind of edge on so it can glide. So it's experiencing a lot of drag during this transonic moment. So yeah, max Q, it is simply dynamic pressure. Also, apparently, there's a couple of bands called max Q. There's literally 2 of them. There's like a group of astronauts that apparently go under that name. And if any of you remember Michael Hutchence, he was the lead singer of NXS, Need You Tonight and all that. Dead now. He had a band, he had a project in the 80s, 90s called Max Q. Yeah. Anyway, moving onwards. Russell Nelson also had a secondary question. He was asking, to raise an orbit, the engine is fired at apogee and perigee. Is it exactly then, or slightly before raising and slightly after? Well, so yeah, basically, if you have an idealized, perfect, impulsive firing of an engine firing that takes 0 time, then you want to put it exactly on the perigee to raise the orbit, and then when you get out to the apogee, you want it exactly on the apogee to circularize it. Now, real engines aren't like that. They take a finite amount of time, and the approximation that we always would use in Kerbal Space Program is roughly 50% ahead and 50% after. Actually, you should move it slightly earlier because most of your thrust happens towards the end of a thrust pulse because your mass is dropping. So the acceleration during an extended burn actually increases over time. And if you want to get 50% before and after, you actually have to shift it a little to the left. Point is, yeah, you want to try and get this right in the middle of the burn. There's a second problem if you have a very low thrust engine, where if you're trying to maximize, say, your apogee raising, if you literally take too long to get maximum efficiency from it if you just fire it in one pulse, right? So if, say, you're going to find that to get the delta V required is going to take 45 minutes, say, that's like half an orbit, and that means that during half that orbit you're actually getting less efficient, less use of the Oberth effect, because after you start initially burning, you accelerate, you start to get higher up, and for low thrust you actually end up losing energy. So the most efficient thing to do, of course, is to fire your engine for a small amount of time at perigee, let the thing come around, and then fire again to raise it further, and keep doing this until you reach your target. So that's obviously trading off time versus number of maneuvers versus the actual performance. And if you're doing astrodynamics, you know how to try to satisfy all those and get the best performance out of your rocket. Okay, David C. Elliott. Hi, Scott. Love your channel. I have a deep space question for you and wonder if you'd thought of an answer for it. What if SpaceX cut the Starship into two pieces to allow for separation of such and added a small propulsion unit to the third stage? Considering the mind-boggling power of the stack, it seems like a quicker solution to the lunar mission would be a way to do it unrefueled. Thanks. So yeah, what you're actually basically asking is making a three-stage Starship with the third stage launching from Starship. Look, at this point, the main thing that is really going to limit them is developing hardware, I suspect. Now, yeah, you could put like, what, 100, 150 tons in a Starship and launch that. Roughly saying, by the way, the upper stage of the Saturn V, the chunk that was actually injected into lunar trajectory, was about 150 tons, right? So they put about 150 tons, including the third stage of the Saturn V. And then that put the command module and the service module and the lunar module towards the moon. So it's sort of there, but, and they might do this, right? It's totally valid. They could do this. They might choose to do it with an engine that's different from the Raptor either. They might use the Merlin. But fundamentally, they have to develop this hardware. And if they're going to do all this development for Starship, then adding a mini version of Starship that needs to fly to the moon and only the moon is adding extra work. And if they can just make this work with a regular Starship that perhaps loses the fins and gains some landing engines, then that minimizes the number of changes they make. But maybe they look at this and they say, look, we have to make all these engineering changes anyway. This could totally work. So yes, it is absolutely the most efficient way to do it is to have an actual three-stage rocket and launch that, but it's a lot of extra engineering, and the question is, does the break-even point in terms of time spent designing new hardware versus time spent qualifying said hardware for sending to the moon? Yeah, is refueling the thing that is going to make Starship take longer than anything else? How much time? Ideally, I think SpaceX would like to develop the refueling anyway. They need to develop that refueling. So if they can do it as part of a NASA project, that would be better for them. Matt Evans says, my question is how likely we are to see muon catalyzed fusion, and how realistically is it as a source for spacecraft propulsion? Well, fusion as a source of spacecraft propulsion would be fabulous. And yes, problem of course with fusion is it needs high energies, high temperatures, high densities so that you can squeeze the hydrogen nuclei close enough together to make them fuse. The idea with muon catalyzed fusion is that, so a muon is basically like an electron, but it is about 200 times heavier. So an electron and a hydrogen or a deuterium nucleus, if you pair them up, they're a certain size. And if you try to squeeze them closer together, it's the electron around the atom which is actually pushing back and stopping the cores, the nuclei getting close together. So if you have an electron or a muon which is 200 times heavier, that makes your atom 200 times smaller. And that means that fusion is much easier because your nuclei are already closer together. In fact, the math suggests that you can have fusion at room temperature, i.e. cold fusion, by shooting muons into, liquid deuterium and tritium all together. The problem is muons are not stable. They last about 2 microseconds before they decay. So you have to generate them, shoot them into this, and then hope that they catalyze enough reactions to pay off the energy that's required to generate these. And you can't really tune a particle accelerator to generate just muons. At least, maybe someone's figured out a way of doing it, but generally in particle accelerators, you create these particles by slamming things into each other and watching the stuff spray out. And maybe you can tune it to the right energies and get, the resonances to get muons to be your preferred thing coming out. Maybe you generate, I think actually what they do is they generate a stream of pions, and then as those neutralize, you end up getting muons out. But point is, this end of the process takes a whole bunch of energy, and you need hundreds of fusion reactions to happen, like 500 maybe, before you equal the amount of energy that it takes to generate those muons. Then you need to add in energy conversion efficiency, and that's going to take some amount of, you're going to lose some energy there. Instead of getting electricity, you get heat. And then out of that power, you have to feed that power back into your muon beam and the rest of your process to keep the thing running. So generally, most people that have studied the problem think that muon catalyzed fusion can't break even in any way. One of the problems is that while you can get the reaction rates to be high enough, the problem that occurs is the muons will sometimes pair up and instead of pairing up with hydrogen nuclei and bringing them close together, the muons will pair up with an alpha particle that is speeding out of the mixture. And that means your muons are essentially lost to the reaction. And the time that you have, it's wasting its lifetime trying to make this this helium nuclei fuse with something, and it's not going to happen, right? I'm sorry, no one wants to mate with you. There's other issues where, there's all sorts of other issues surrounding this. But basically, as far as I know, nobody has come up with a reliable way of making it break even, and you would want it to do more than break even so that you get the energy out in a useful manner. I mean, if you think about it this way, if you've got a spacecraft propulsion system which is able to generate a certain amount of energy, why would you want to increase the reaction increase the mass of the particles and get lower specific impulse? Well, I don't know. Anyway, yeah, fusion would be great. I'm not holding my breath for cold fusion anytime soon. Interesting side note, by the way, I do remember Arthur C. Clarke talking about 2061, which is like the third book in the Space Odyssey series, I guess. And in that, they have muon catalyzed fusion drives. But I remember him talking about a conversation or whatever he had with Alexei Leonov, and how Alexei was kind of worried, or he was concerned, I guess, because he was like the head of the Russian Space Agency or the Soviet Space Agency or something. He was certainly very important. And in 2010, the book 2010, the Alexei Leonov spacecraft in that book was powered by a cold fusion drive known as the Sakharov drive. And at that time, in the 80s, when this was written, Andrei Sakharov was a dissident. He, of course, had worked with you to develop the fusion weapons, hydrogen bomb, the Soviet hydrogen bomb, and somewhere along the line had fallen out of favor and said the wrong things. And Alexei Leonov didn't want to be associated with them. But I think that probably changed a bit in the 1990s. But anyway, that was a sort of interesting story I remember Arthur C. Clarke talking about. Okay, Ian Valentine, simple question for your rapid fire. Is the phrase in orbit and on orbit the same meaning? If not, what's the difference? Okay, so as far as I can tell, There is no significant grammatical difference between saying an object is in orbit or it is operating on orbit or whatever. So, as far as I can tell, I've never seen any official style guide, say from NASA, that suggests that one thing or the other should be chosen. Having said that, the place where I see on orbit used is generally in very technical publications, whereas in orbit tends to be preferred by the general public, the general news, science education, whatnot. Yeah, as far as I can tell, there's no difference. One is a subset, is much lower. On orbit is a lot rarer unless you happen to be spending your time reading NASA papers on the National NASA Technical Report Server, such as me. I spend my time doing a lot of that, so I see on orbit a lot. But yeah, I think it's interchangeable and just makes the person feel that they're a little more in tune with what space is doing. Okay, Scott Van Zandt. Hi Scott, from years of playing KSP, I know that aligning your payload center of mass with the center of thrust is super important. What kind of tools and techniques do NASA, SpaceX use to find the center of mass, especially for complex payloads like the transporter missions? So look, for the large transporter missions, they just need to get close to the center of mass as far as I can tell, because the upper stage has pretty good steering capabilities. It has a nozzle that will vector and control itself. So they don't need to worry too much because it's all actively stabilized. But there is a lot that needs to be done if you're building a spacecraft that needs to rotate correctly and stably. They have these things called spin balance testing hardware, where you put your satellite on a turntable and you can, by rotating it, you can actually figure out where the center of mass is because it will want to wobble. And so then you can add in ballast and zero this thing out. You saw this in my video about the Syncom and the Telstar satellites, where they had to balance the satellite on this spin stabilized upper stage. Now, spin stabilizing or spin rotating the satellite to actually verify it's stable isn't perfect. There are actually problems. One of the things that can happen is because you're spinning in an atmosphere, you're actually adding drag, and that adds air pressure because you're rotating. And if your spacecraft is asymmetric in some way, then you're going to get forces from that drag. So you want to rotate it fast enough that you can detect that it's off center, but slow enough that you're not actually getting any problems. You could put it in a vacuum chamber. That will certainly solve a lot of problems, but yeah, then that adds a whole lot of complexity to your balance. Another thing that can happen is if you have fuel tanks on it and you've got propellant in those tanks that are partially full, they will, of course, the rotation will pull the fuel out, or the liquids out to the outside, and that means that your center of mass shifts around a little, and you may need to account for that. There are new balance systems that just feel the weight via various other sensors, but yeah, it's really a thing about satellites most of the time as far as I know. And for the transporter missions, I think they just get it close enough because there's too many random things that needs to be here and there. Okay, David Foot. Hi Scott, I hope all's well. Wonder you might have an idea what I observed 2 nights ago. I'm an airline pilot, was northbound through the night from Lagos, Nigeria to London. That would be a cool thing. For pretty much the whole time over Nigeria and southern Algeria, we observed at least 4 lights that varied in intensity from barely visible to as bright as Jupiter in a similar manner to the original satellites. Okay, and the lights remained in a loose cluster always to the north of us at an elevation perhaps 10 degrees above the horizon. I assumed that they were satellites, but their position didn't change over time as we observed them, which in my mind would mean that they too were moving north. I was convinced that they did have movement relative to each other in all directions. Their altitude appeared to be LEO, and this would have been about midnight on 4th of July. Okay, so look, I actually picked this question because I have had a bunch of other people ask me about very similar sightings. This is where you're looking to the north in the middle of summer and you're seeing these satellites flare. And I'm pretty sure these are Starlink satellites. And they're not in the usual place, so people discount them. And we're also not seeing them moving across the sky. So obviously, you can only see like a satellite when it is illuminated by the sun. And typically for me, standing on the ground, I will look out to the west just after dark and I will see a bright satellite appear, fly over towards the east because that's the direction it's going, and then blink out as it passes below the horizon. But looking to the north, you don't expect that because the sun isn't to the north, the sun is to the west. But in the middle of the summer, you're looking towards the pole, and actually because of the angle of the Earth, the obliquity of the Earth's axis of rotation is the correct term, looking north when you're at sufficiently high latitudes, you're potentially seeing the sun in that direction. Now, of course, typically you have to get up to the Arctic Circle for this to actually be relevant, but I think you could probably see satellites that were high enough up, even as if you were as far south as like Nigeria, southern Algeria. I would have to do the math on this, but this is not the only time I saw this, because somebody actually sent me a video where they had a camera that was doing a time lapse of the polar stars, and they could see these satellites flaring just at the horizon. And so this, I think, is Starlink satellites coming over, and you've got the sun on the side of the pole, it hits the bottom of the satellite and reflects down. If they are exactly lined up with the sun, you're going to get this flare. And because it's the middle of the night, they're not orienting themselves to make sure that they're not reflecting straight down to the surface. So I think this is what it is. Starlink satellites in their normal orientation, where the sunlight comes up, reflects off it, and comes down. And if you happen to be aligned in the right place, you can see this reflection flaring as they pass through. That's my theory. And yeah, this is not the only person who has asked this question. Daniel Llewellyn, good morning, Scott. I work in metrology in the semiconductor industry. Oh boy, I bet you have some great stories to tell. We can use all kinds of things to find characteristics of material. I had a thought during a Delta IV launch this morning. Do you think it would be possible to know what fuel a rocket is using by analyzing the sound? And in the case of the Delta IV, you probably could. Because back when I went to the final Delta IV Heavy in California, I actually talked to people that were recording sound, and I did make some discussion about this. So the Delta IV crackles like no other rocket. And the reason for this is because when you have a jet of gas coming out and it interfaces, so the jet is moving fast, and then on the other side is the atmosphere, which is staying still. Then it forms this sort of wobbly boundary that develops into these, eddies. And that's the Kelvin-Helmholtz instability, I think that's what it is. And it turns out that this develops harder and faster if the velocity difference is greater. And for hydrogen, that is the highest specific impulse, therefore the highest velocity. Therefore, the loudest, crackliest rocket engines are pure hydrogen. That's what I thought the Delta IV has. Anyway, so I think there is a definite difference in sound between a pure hydrogen engine and then, say, a kerosene engine. The other thing that is very apparent is that the sound of a solid rocket motor is very different from the sound of a liquid rocket motor. And I'm pretty sure this is down to the particulates that end up coming down in the exhaust, and they get entrained faster and they change the sound. I think there's like more white noise, less crackle when I'm hearing these solid rocket motors going. So I'm sure you can pull some quantifiable data from the audio. I think it would be one of these things where you have to perhaps train an AI or train somebody that knows how to look at these things. But having said that, it's a lot easier to just look at the rocket and see the color of the exhaust to give it an idea about what is flying with. I'm not sure there's any case where you need to know the sound beyond it being cool to know this kind of thing. Okay, so yeah, I think I have to stop this here. But yeah, if you do have questions to ask, as always, post them over at Patreon. I'm going to try and make sure I set up a new thread for this, and please put the questions in there, because I have unanswered questions all over the place that people ask me about. And yeah, I have only so much time, but I always have time for my people at Patreon. I'm Scott Manley. Fly safe.